Yes, thanks, Taylor. I'm Yanlin from CW and QSoft. Today, I'm going to present our recent work about finding top eigenvector. But before that, I need to do a slightly modification for our title. Check this. Yes, we improve our result from finding a top eigenvector to eigenvectors. This is the joint work with Andras Gilliam from the Renning Institute and Ronald de Wolf from the CWI QSoft and the University of Amsterdam. So let's get started. So first of all, in this talk, I would like to stick to the following notation. We will always use the capital A as a D by D Hermitian matrix with operator known at most 1. And our goal is just to find the top eigenvector of it. And we will use, say, phi I and lambda I for the eigenvector and eigenvalue. And they are ordered in terms of the absolute eigenvalue. So what's top eigenvector? So by definition, it's just the eigenvector with the largest absolute value. And there might be multiple of them. Now you might ask why we care about top eigenvector, because there are lots of applications of it, including page rank, principal component analysis, feature linear discrimination, and the ground state of a quantum energy. And the space here is too small, I cannot list all of them, but you can believe me, this is actually a quite important question. So how can we find the top eigenvector? The most straightforward way is to find all eigenvectors by diagonalize the whole matrix. But it sometimes overkills because you will sort of need the matrix multiplication time. So the question, can we do better if we only want to find the top eigenvector? And the answer is yes. Suppose there's a reasonable gap between the top and the second eigenvalue. So in roughly 100 years ago, by Hermann Mills, he proposed an algorithm called power method. The algorithm goes the following. At the very beginning, you generate a uniform vector, and for each iteration, you apply the matrix A onto this vector, renormalize it, and do this over and over again. And at the end, this algorithm will output a good approximation for the top eigenvector. And let's see why this algorithm works. At the very beginning, you can write your W0 as the sum of the eigenvectors. After apply the matrix A, the corresponding eigenvalue will jump up in front of the corresponding eigenvector. And if you do this, say, k times, it will be a lambda j to the k in front of the vector phi j, right? And as I said, we assume there's a gap between the top and other eigenvalues. So when k is large enough, then the final output after renormalize will be a good approximation for the top eigenvector. And precisely, if you choose your capital K as large as, say, order 1 over gamma, then it's good enough for approximate the top eigenvector up to the global phase. And now, if you look at the algorithm, for each iteration, the only thing you have to do is to apply the matrix vector product. So now you already have an algorithm which don't really need, say, d to the omega 10. You only need the d squared 10. Then you can find the top eigenvector. Okay. And moreover, this algorithm is actually sort of robust against some benign error. And we would like to thank our friend Xinbo Wang for pointing out the robustness of power method here. Without him, we don't think we can finish this project. And here is the robust power method, as known as the noisy power method. This power method, noisy power method, is proposed by Hub and Price in 2014. And the only difference between the noisy power method and the normal power method is, for each iteration, they include an error GK. And Hub and Price found if this GK is sort of benign, that is not too bad, then at the end, by using the K roughly still the order 1 over gamma, you can still find a good approximation for the top eigenvector. And what does the benign errors here means? The benign error means you have small Euclidean norm, and the second, you should have a small overlap with your top eigenvector. And in other words, you would like to expect your error to be sort of sub-Gaussian, or you would have a small second moment bound. So here's the question. Can we have a quantum speed up for the noisy power measure? Or on the other hand, because you look at the algorithm for each iteration, only thing you have to do is to do the approximate matrix vector product. So the question, can we have an approximate matrix vector product first by using the quantum power? And the answer is, of course, yes. Otherwise, I will not stand here, right? And so before we go to our result, we would like to carefully introduce our computational model. So in our computational model, we assume the entries of matrix A are all stored in the quantum readable read-only memory, that is QRAM. And we also assume we have a classical computer, of course, and also we can code some quantum subroutines. And we also assume we allow to use the quantum readable classical writable classical memory, QRAM or QCRAM. I know some people might be suspicious about the assumption here, but because I am theoretic, so I will anyway fine with this assumption. And at the end, instead of outputting a quantum state, we would like to output a d-dimensional vector classically, which approximates the top eigenvector. And our time complexity counts the number of classical operation, and the quantum gates, and also the number of the queries to QROM and the QRAM. And here's our result. Like what we say, for classically, if you want to approximate the top eigenvector, there is a power measure, which is d squared, upper bound. And for the lower bound, in our paper, we also show a classical d squared query lower bound. But we think it's sort of elementary. It must be written somewhere else. So we did not sort of claim any novelty here. And we would like to focus on the quantum tight upper and the lower bound here, which is d to the 1.5 for the upper and the lower bound. And please note that during the talk, when I talk about upper bound, I always mean the time complexity. When I mention the lower bound, I always mean query complexity. Okay? So, okay, I will wait here for 5 seconds for people taking picture. Okay, now let's go to our measure, this upper bound. So as what I said, if we want to speed up the noisy power measure, it suffices to speed up the approximate matrix vector product. And we would like the approximate output of the approximate matrix vector product to have some benign errors. And precisely, suppose we have a matrix A and a vector W, we would like to output an estimated mu such that the difference between AW and the mu is small in terms of Euclidean norm, and is further, say, 1 over square root of d with other arbitrary unit vector. So in other words, we not only want this error to be small in terms of L2 norm, but also it should be sort of roughly uniform over every direction. And in our paper, we propose 2 different methods for achieving this. The first method is called discrete quantum Gaussian phase estimator. And by using this, we end up with a d to the 1.75 ton quantum algorithm for doing the approximate matrix vector product. This is provably better than the old classical algorithm, but this is not optimal. We still include this because we think this is a more elementary tool, and it looks quite cool actually. And our second method, which achieved the near optimal upper bound, is called the time-efficient unbiased quantum state tomography. And we end up with a d to the 1.5 plus small o1 ton. And as I said, it's near optimal because we show a d to the 1.5 lower bound. Okay, now let's see the first tool, which is the quantum discrete Gaussian phase estimator. So let's quickly recall what happens in the quantum phase estimation. So in the quantum estimation problem, you will give the unitary u and the quantum state k precise. Your goal is to estimate the theta of exponential 2 pi I theta, right? And in the textbook, we learn the algorithm starting with the uniform superposition and apply the control unitary on it. After that, by doing the quantum Fourier transform and measure it, we will have a good estimator that is with high probability. Its additive error is sort of small. And what happens in our discrete Gaussian phase estimator, instead of the uniform superposition, we prepare the discrete Gaussian state at the very beginning. And after apply the control unitary state, we will have the corresponding phase jump in front of the corresponding computational basis. And again, by applying the quantum Fourier transform, we will end up with a new discrete Gaussian distribution with peak at theta. But its standard deviation is capital N over S. So after measure this and after some reasonable rescaling, we will end up with an estimator with a small sub-Gaussian additive error. And now you might wonder how we can use this to do the approximate matrix vector product. So this is how we do. So the idea is we first encode the row of matrix A in the product between the row of matrix A and the W into the phase, and then we do the quantum discrete Gaussian phase estimator, which takes d to the 0.75 time. And we do this for each entry, which is totally d entries, and therefore the total time complexity will be d to the 1.75. Now, let's go to the second method, which achieves the near optimal upper bound, which is the time-efficient tomography. So what's the tomography problem here? We now have the state preparation unitary U of a quantum state per psi. Our goal is to learn the classical description of this per psi. And in our paper, we improved the previous result by from Approximating, Cornelissen, Guillen, and Nachinishi in 2023. We have a time-efficient, unbiased quantum state tomography. And this time complexity essentially matches the optimal Curie complexity, which is sort of essentially tight. And let's see how we can use these tomography tricks to have a good approximate matrix vector product. So first of all, we implement a block encoding of A and then apply this to the quantum state KW. And by using Ross result, we know the cost of implementing the block encoding of A is just a square root of D. And by using our result, we know by using say only D over epsilon applications of unitary, we can have a good estimation for the quantum state AW. And if you multiply those two together, you end up with a D to the 1.5 over epsilon time quantum algorithm for estimate the approximate for approximate matrix vector product. Now, let's put it back to the noisy power method as well as some QSVT tricks. We immediately have a D to the 1.5 over gamma epsilon time quantum algorithm for estimate the top eigenvector. And we further generalize this result to approximate the top Q eigenspace using only roughly Q extra overhead. And one thing worth mentioning here is in our algorithm, we really don't need the state preparation unitary. It suffices for us to make use of the reflection through the quantum state. And that's the end of upper bound. Now we are ready to go to the lower bound. And as I promised 5 minutes ago, I say we have a D to the 1.5 lower bound. And let's see the hard instance of this lower bound. So the hard instance we consider here is actually a rank 1 matrix with plus lots of Gaussian error. And the rank 1 matrix is UU transpose, where U is either -1 or 1. And the entries of Gaussian error noise is just the loss noise with mean at 0, and the variance is in the order of 1 over D. You can equivalently consider the matrix is just like the Gaussian distribution with mean at either 1 over D or -1 over D, but its total its variance is always in the order of 1 over D. Now, if you use some random matrix theory, you can immediately see with high probability the spectrum gap of this matrix is actually constant. So because the spectrum gap is roughly constant and because U is either -1 or 1 to the D, then if we want to recover, say, 99% entries of this U, it suffices to find the approximate top eigenvector. So if we have a low bound for this problem, then we will have a low bound for approximating top eigenvector. Okay. Now, you might wonder why this problem is hard, right? So let's see a classical example for the high-level intuition. So if we want to learn, say, one entry of this U, you will have to distinguish two Gaussian distribution, one mean at 1 over D and the other mean at -1 over D. But its standard deviation is roughly 1 over square root of D, which is much, much bigger than its mean. So if you calculate the total variation distance between those two distributions, you will know you really need, say, D queries to distinguish those two distributions. And like I say, we want to learn 99% of this, the 99% of entries of U, right? So in this case, you will need to learn 0.99D entries of it, which takes you D square lower bound. Of course, you need a more careful argument, but for the time issue, I will not mention here, but this is the high-level idea. Now, what happens for the quantum lower bound? For the quantum lower bound, what we do is suppose we have a capital T quantum algorithm to recover, say, 99% entries of U. Then, by some using averaging argument, we know there must exist a super index I such that you only need, say, capital T over D, many quantum query mass on the ith column and row. Then you can learn this corresponding UI correctly with high probability. So to show a lower bound for learning, say, 99 entries of this factor U, it suffices to find a good lower bound for learning this UI. But like I say, if you want to learn UI, you need to recover the UI from the two Gaussian distribution, with the mean really close, but the standard deviation really huge, right? And now you also allow the quantum algorithm to have a superposition query. So things got slightly complicated. So I will not provide the detailed proof here, but at the end, we can show the square root of the quantum query is needed for learning, say, UI. So plugging back, we will end up with a D to the 1.5 lower bound. And here is the quick sketch of how everything works. So if you want to show such kind of square D of lower bound, we use the weighted as the first method with some technical modification. But the idea is we find a joint distribution mu on pairs of matrix, and the corresponding distribution, marginal distribution x and y, are conditioned on the UI equal to 1 or -1. And like everyone does in the first trimester, we start with a progress measure 1, end up with a progress measure less than 1/2. Now, we just calculate the expected per query progress is roughly the expected Hamming weight over D. And by knowing the expected Hamming weight between x and y is roughly square root of D, we then immediately know the per query progress is at most 1 over square root of D, which means we have a square root of D lower bound for this problem. By plugging this back, we immediately have a D to the 1.5 quantum query lower bound for learning the top eigenvector. Okay, so here is the summary and some future works. Like I say, in our paper, we provide two faster quantum algorithms for doing approximate matrix vector product. And both of them implies a faster quantum algorithm for approximating top eigenvector. The first method is a quantum discrete Gaussian phase estimator, and the second method is a time-efficient unbiased quantum state tomography. And here is the table for our result. compared to the classical result, to learn the top eigenvector, we end up with a d to the 1.5 over gamma epsilon upper bound, while we also show a d to the 1.5 quantum query lower bound here. And we further generalize this to learn the top Q eigen subspace by using extra Q overhead. And here's some future work. First of all, can we use our approximate matrix vector product to end up with a faster approximate matrix space product algorithm? And the second is, if you look at the classical algorithm, you can see the gap dependency, gamma is 1 over square root of gamma instead of 1 over gamma. So can we further improve our quantum algorithm to have, say, 1 over square root of gamma dependency? And the last is, can we have a quantum lower bound for learning the top Q subspace or finding the top Q eigenvectors? And that's all my talk. Thanks, everyone.
We have some time for questions, so please step up to the mics in the middle.
Thanks for the great talk. My question is, do you consider the sparse case, that is the matrix sparse, and what is the result compared to the classical ones?
Yeah, so in our paper, it's not on the archive. We will soon upload to archive. But in our paper, we also include the sparse case. That is, you allow the sparsity query. And in this case, the d to the 1.5 will end up with d times square root of s. Yeah, this is the corresponding result. Yeah.
Thank you very much.
Thanks.
Yeah, so I understand how you got how you can get the eigenvalues by phase estimation, right? But I didn't understand how you got the eigenvector to the biggest eigenvalue. Can you go back to that slide? It was just too fast.
Yeah, I think at the end, you don't really need to know the largest eigenvalue because power methods sort of help you to learn the top eigenvector without learning it. Yeah, so.
Okay, so you're
Yeah, so maybe just go to the power method. The only assumption you need is there's a reasonable gap between the top and the second eigenvector. Then by doing this, you will end up with the good approximation for the top eigenvector. You don't really need to know the eigenvalue in this case. But of course, in our paper, we also include some results for estimating, say, top eigenvector or top Q eigenvalue, top eigenvalue or top Q eigenvalue, given there's a reasonable gap between the Q's and the Q plus 1's eigenvalue. Yeah, something like that.
Okay, so you're multiplying the matrix A to the power K with the vector. Yeah. But how do you get that done? Is that done with the phase estimation in terms of like to directly get the A? Are you kind of making a measurement or something so that the A comes in front, or?
Sorry, I don't.
Yeah, maybe we have to talk about it.
Yeah, okay, we can talk about it. Yeah.
Thank you. Finding the top eigenvector for Mission matrix, I guess also it allows you to find the bottom eigenvector of a Mission matrix, which is the ground state of a Hamiltonian.
Exactly.
Which I think has been studied a lot before, also using phase estimation to prepare the ground state, for example.
Yes.
And maybe using qubitization, which would allow the same kind of query access models. So my question is, do you know how it compares to other algorithms for ground state preparation of Hamiltonians?
Yeah, I think for the ground state preparation, Hamiltonian, it's sort of like you want to prepare quantum state, right? But here, our output model is we want to know the classical description of the eigenvector. So it's not exactly comparable, to be honest. Yeah.
I see. Thank you.
Hi, I was just wondering if there's a way to generalize your method to find an eigenvector in the middle of the spectrum as well.
Yeah, so it's typically if you have a matrix A, which has operator known at the most 1, then you can consider something like identity minus say 1/3 A, then you can do the same thing, exactly. Yeah.
Cool, thanks.
Okay. If there are no other questions, let's thank the speaker again.